Hello, students. We are into chapter 12. Now, in this chapter, we're starting to do more with shapes, and in this particular chapter, dealing with congruence. How do I know that two shapes are exactly the same shape? And we'll also talk about, a little bit later, not in this section, but we'll talk about whether things are similar, which is the same shape, but maybe not the same size. So we're going to talk about that in this chapter. We've got the Common Core standards up here. Students should be able to draw, construct, and describe. They should be able to solve problems involving scale, and they should be able to draw with a ruler and protractor and technology or freehand geometric shapes with given conditions. And let's take a look. We're going to see, notice, sometimes when we give conditions, and we'll do an activity in class about this, the conditions determine a unique triangle. Other times, maybe they don't give you enough to determine a unique triangle. What they give you is enough, maybe there's multiple triangles, and occasionally we'll see that there is no triangle possible. All right. So one of the objects that we have here, this is kind of a fun one, it's called a reptile, not like the reptile, like a lizard or anything like that, but it's a replicated tile. And so this shape, what you can see is as they cut out certain pieces, the cut out pieces in one become the openings for the other. And you have this really cool, looks like puzzle pieces coming together. When in reality, we'll get a chance to do this as well. We can use tiles or tessellations to build things like this. Let's talk briefly. Congruent. Terminology-wise, congruent is objects that have the same size and the same shape. However, similar is they have the same shape, but maybe not the same size. When you take something like a photocopier, think about that. Put something on a photocopier, you say make a photocopy. If you leave everything the way it is, it makes a copy that is exactly the same size. That shape would be congruent. It's a different object because it's a copy that came out, but it has exactly the same size and shape. If you take that same copier and you say, I'd like something to go that's 50%, then it produces a copy, but at a different size. The same angles would be in the shape, the same kind of general shape, but it's not going to match up perfectly. And so that's the difference. I want you to think about that with like a photocopier. If you make something bigger, you make something smaller, you preserve the general features of the shape, but the size would change. And that's the idea between similar. Okay. Let's take a look at that in context with some of our shapes. Here we have circles. So we have two circles. If the circles, which again, the circle is a shape, if they have exactly the same size, right? So that means the radius or some type of measurement about that would be exactly the same. We would say the shapes are congruent. But in this case, what you can see here for the two stacked right over each other, part A, one of them definitely has a bigger radius, which means these two shapes would be similar, but not congruent. Over here, these two shapes right here would actually be exactly the same size because the radius is identical. And that means these two shapes would be congruent. Okay, so when we build things with our compass, as long as we don't change the length uh, between the pokey part and the lead part, as long as we don't change that, we are creating congruent circles because we're creating congruent segments. Okay. So two line segments are congruent if and only if one can fit right on top of each other, which we're going to kind of formalize here. Two segments are congruent if and only if they have the same length. Okay, now we can check length by just using our compass now. We just widen it out this one, go over and check the other one. I don't need a ruler. See, it's not saying I have to measure that. It's just that it has to be exactly the same. Okay, and two angles are congruent. And you notice the symbol for congruent has a little squiggle on top. So just so we're all making sure of what we're saying. So let me jump in here and write this down. So when you have this symbol equals, this refers to numbers. When you have this symbol, which is like equals, but it has a little squiggle on top, this symbol is for congruent. The one up here is for equal. Okay. So we use congruent when we're talking about shapes that may not be in exactly the same place. Like up here, we had two different lengths. They were in different places, but we saw that the lengths were equal. We could also say that OA as a segment would be congruent to O prime B as a segment. Okay. And again, the segments are congruent if and only if the lengths are the same. All right. Now we're going to get into the idea of geometric construction. So we use this frequently in many different areas. In our class, we're going to be using a couple tools. You can see it here listed as a compass and a straight edge. And this was, again, from back hundreds and hundreds of years ago. We will also be able to use some technology, thankfully, which will give you the opportunity to see how to do this if you don't have a compass and a straight edge. And so that's the idea. So these are the manual tools, the compass, the straight edge. And again, typically, these days, we don't just use a straight edge. We use something that has marks on it, which would identify it as a ruler. And even sometimes now you'll see people still pull out an old triangle, and a triangle will have built-in angles as well as straight edges. So it's kind of a nice piece. It gives you some nice ratios. All right, let's see here. Here are the construction rules. If you have 2 points, a unique straight line can be drawn containing the points, as well as a unique segment that creates the points. So if you have 2 points, you can draw a line between them, or you can draw a segment. A circle can be drawn if you have a center and a radius, okay? Because that center will be the pokey part of your compass. The radius will be the distance between the pokey part and the lead part. And as you turn it, you'll be creating a circle. Any number of points can be chosen on a line, a segment, or a circle, any number. Points of intersection, that's how we create more points, is we intersect lines, circles, or a line and a circle. And once you find those points, you can use those to create segments, lines, or additional circles. Okay. So compass and straight edge constructions, again, you get a little bit of error, but that's because like the lead starts wearing down. And a geometric line is a good idea. Think about that idea of a line as having 0 width. But whenever you draw a line, just as a way to visualize it, there is definitely a width there from however thick your pencil lead is. So, but we think of that as, okay, we think of it as having no width. Okay. All right. Then they say figure 3 shows how to mark off and duplicate lengths to construct circles or arcs. So if you have a point O and you have some length you want to replicate, set your compass, like I showed in the setup video, to replicate that length. Then put the pokey part or the pointer at the center, and then hold the pointer at O and move the pencil to draw the circle. Now, again, if you're trying to do this with 2 hands, it's going to be very, very challenging because you're trying to like push one down while you keep the other one moving. It's just really hard. Work to tip the compass down, keeping pressure at the pokey part, and then doing a quick turn. And we'll practice this in class as well. Okay. If you want to construct segments, you have to have a segment length in mind. Again, use your compass to copy the length and then transfer it over to a line. Now, the way I don't think they didn't really say here, there is no line listed on point L. But remember, one of the rules is you can create as many points as you want on a line. So draw point C because that becomes the center like we saw in the picture above. So draw point C, then put the pokey part at C, then turn, and where the intersection occurs, that is point D. So I will demonstrate these with the compass and straight edge here in a moment. I want to get through a couple other pieces, and we're going to talk about triangle congruence, which again is uses these pieces that we've got here. Okay, so here's the thing. If you want a triangle to be congruent to a different triangle, here they have used prime numbers like an A prime or a tick We call that prime A prime, B prime, and C prime. And if we want these triangles to be congruent, you have to remember that means same size and same shape. Then what we need is, this is the if and only if, we need angle A to be congruent to its corresponding piece, which would be A prime, B to be congruent to B prime, C to be congruent to C prime. We need AB as a segment to be congruent to A prime, B prime. Okay, that's marked with one tick. We need BC to be congruent to B prime, C prime, and we need AC to be congruent to A prime, C prime. You can see those marked respectively with 2 ticks or with 3 ticks along the sides. So just so we're clear, a triangle really has 6 parts. It has 3 angles and 3 sides. And this definition says, if you want to say the triangles are congruent, every part has to match. You can't match on 5 of the 6. You can't match on 4 of the 6. All of them have to match. And what we'll see in class is, while this is the definition of congruent triangles, there may be times where with less information, we may still be able to build congruent triangles. And our goal is that if we can build congruent triangles with limited information, that we pick up for free all of the other pieces. And we're going to start abbreviating a little bit here, but this is the cool thing because it's if and only if. If you know the triangles are congruent, then all of the corresponding parts have to be congruent. And so that leads us to this statement right here, which we're going to use repeatedly. So I am going to highlight this. Okay. Corresponding parts of congruent triangles are congruent. And we're going to abbreviate that as CP, CT, C. Corresponding parts of congruent triangles are congruent. Notice that that does mean we have to have congruent triangles first. We need congruent triangles. So you cannot use this unless you have congruent triangles. Right? There's a little bit of an example here, and then we get into some different congruences that are possible. And we'll also see these in class. I'm going to go over them kind of quick because we are going to do an in-class activity about these. If you know the 3 sides of a triangle are exactly the same, then you do not need to know anything else. If the 3 sides of one triangle are congruent to the 3 sides of a second triangle, the triangles are congruent. Notice that means I only need to know 3 of the 6 pieces, but I get the others for free. Okay. So now they're saying this is what's known as an axiom, which means you do not have to try to prove this statement because we can see that it is true in general. So that is an axiom. All right, so that means side, side, side. If you can match up 3 sides with 3 sides of another triangle, the entire triangles are congruent, all of the other pieces. Okay. Then we go through what's known as a construction, and this is one we're going to do in class. We take a given triangle, we create another triangle. And the way that we do this is by capturing lengths. So I'm going to demonstrate how to do this so that you can kind of get the idea of it. And also, it does lead to how we can construct angles. And being able to construct an angle is a little bit more challenging than just doing a side, but I think you'll see the reason why the angles turn out to be congruent is we're going to build triangles. And when we build triangles, especially congruent triangles, we can use things like side, side, side to say, aha, the corresponding pieces must be congruent. Now that's going to lead us to things like side angle side congruence. And I'm not going to go through all of these components at once, but side angle side angle side congruence is listed as a theorem because we can prove it using side, side, side. Then you have a few examples of that. In this first section, we'll also talk about a right triangle, which is a very specific type of a triangle. So if you have a right triangle and you know one leg and one hypotenuse, that's the long side, then you've guaranteed that you know the other. Now, this is a very special case because it may not always be true that if you know two sides and the angle not between them, it may not always work. But there's other properties for a right angle that make this true. So in general, the way the book has worded this is that side-side angle does not always hold true. And they're correct, and we'll see this in class. I like to write it as ASS, angle side side, because typically when you see that word, you don't want to say it because it's like a bad word, and that might help remind you, hey, bad word, bad math. We can't guarantee that we'll have congruence. If the angle is 90 degrees, that's a very special case. In that case, yes, we can guarantee congruence, but that's only because of some of the properties of a right triangle. Okay. All right, let's finish it up. We get some beautiful things with isosceles triangles. And with an isosceles triangle, we can actually get something called a perpendicular bisector of a segment. And we can see through folding, and we'll also do it with construction, that this beautiful line called a perpendicular bisector creates congruent triangles. Because it creates congruent triangles, we get a whole bunch of other features. The theorems listed below are very, very important. And that basically, this one, the first one says that any point that is equidistant from the endpoints of a segment. So if I take my segment to be BC and I pick any point in the world that is the same distance from B and the same distance from C, that point is going to lie on the perpendicular bisector. So if I think these are the same, the point I just created has to lie on the perpendicular bisector. And if you pick any point on the perpendicular bisector, guess what? The length of these two pieces right here will be exactly the same. So if you pick a point on the perpendicular bisector, then it is equidistant from the endpoints of the segment. If you pick a point equidistant, then it's on the perpendicular bisector. So this is like a two-way street. This is like a biconditional. Okay. And because we get all those cool features, right? Because when I draw this point right here on an isosceles triangle and I build a perpendicular and it has to bisect, I have created an option. Well, I have actually a few options here. I could use the middle side by itself and say by side, 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 the two triangles, one right here and the other right here, these two triangles end up being congruent. Now, if they are congruent, then the corresponding parts are also congruent, which means angle B and angle C, which are corresponding angles, those have to be congruent. And that's what you get down here in theorem 12.4. It says the angles that are opposite the sides that are the same in an isosceles triangle, those angles have to be the same. And that also means that if I came up here to the top, let me erase, it's getting a little bit busy here. But if I came up to the top, this angle up top would have to be the same as the angle right next to it because those would correspond. And if that's true, then this line, which we made as AD, it is a perpendicular bisector because it cut the side right in half. But guess what it also does? It also cuts the angle A in half. So it is also an angle bisector. So the angle bisector of an angle with two congruent sides lies on the perpendicular bisector of the third side. So that is pretty cool stuff that we'll actually use, and we'll get to see why when I say it's pretty cool, it's like, yeah, is it? But I think you'll get a chance to see that. All right, last couple pieces here for this section. A triangle also has what's called an altitude. So every side will have an altitude, and that's the height of the triangle when you consider it from the different points of view. So let's take a look at this. I'm going to zoom in a little bit because I want to really, the pictures can be a little bit confusing at times. So what you have to do when you're forming an altitude is I want you to think of, I'm going to go a little bit thicker here. I want you to think of taking any side. I need a brighter color than that. Sorry about that. Here we go. I'm going to pick any side. I'm going to pick the bottom side. I'm actually going to go even thicker just to show. Okay, there it is. There's the bottom side, right? Take that side and take the point that's not on that side. And then from that point, draw a perpendicular line. That line that you create, this segment that you have just built from one point up here down to the other side, that segment is called the altitude. Okay. Now, if you pictured this triangle being like a mountain, like you're looking out and you see a mountain, the altitude references the height of the triangle. Okay. So that's what we're looking at. Now, you don't have to use the same side every time. You can pick a different side. So watch this. If I pick CB as my side, then I need to pick the point that's not on the side. And again, I need to draw a perpendicular from that point to the opposite side. So it goes like this. So again, if you tip your head, if you kind of twist your head a little bit, you can see green being the base. So think about that being the base. And point A sitting above it, then AE creates kind of the height of the triangle if I use BC as the base. So no matter which base you use, you will always have an altitude. Now that gets a little bit complex in obtuse triangles, but that's just because it lies outside the shape. So take a look. So if I was looking at shape, let's see here. I'm going to pick this side right here. And again, the picture gets a little, the reason why I'm trying to go a little bit slower is this picture gets a little bit confusing. I need you to think of AB, and then I need you to think of the point that's not, the point of the triangle that's not AB, and that would be point C. Now I need a perpendicular from C that's perpendicular to AB. And the issue is that AB, excuse me, that AB, while it's a line segment, isn't extended far enough to make this happen. So what you do is you extend AB, creating the line instead of the line segment. And now you have the ability to go from point C and build the perpendicular. So when it doesn't look like there's a perpendicular, it's okay. Just extend the line and then you can make that perpendicular. Okay. So again, if you tip your head and you see this kind of strange shape in the distance, the altitude tells you how far above this baseline, how far above the baseline is point C. That's like the altitude if you're a hiker, or the height above. And we can do this for any side. So I did want to show that because I think sometimes the picture there that they did is a little bit challenging, Okay. So altitude is the idea of the distance between a point and a line, and make sure it has to be perpendicular. And then we get into the construction of a perpendicular bisector. So we talked about a perpendicular bisector a moment ago for an isosceles triangle, and they're going to show you how to do it. I'll demonstrate that, the construction parts. I'll probably make that in a separate video. And then remember, the perpendicular part of it is allowing that every point that meets this kind of perpendicular piece has to lie the same distance away. So that allows us to do some things that are really, really interesting. And for example, if you have a triangle, we can actually build a circle that goes through all of the points of that triangle. That is known as a circumscribed. Just think about the words. Obviously, it's easy to say the wrong thing here. It's not the other thing. Circumscribed has two pieces. One of them is circum, which means to go around. and the other is scribe, which means to draw. So if you want to draw around a triangle, we're making a circle that draws around the triangle. That's what the word means. We'll also see one that is inscribed, but that goes inside of the triangle. And we'll see how we build those. Okay. So that's the construction. And they did show kind of how you could use something like this. So if you only found a shard or a piece of pottery, you could use this technique to figure out how big was the bowl, even though all I have is a shard, even though I only have a piece. And so we can actually find where the center would be. Okay, so that's it for 12.1. I'm going to make a second video where I go through the construction pieces, which is separate than the concepts in my mind. So I'm going to make a second video for that, and hopefully this gets you on the right track. All right, off you go.